Hello and welcome to the Building Biology Poddy, where we talk about better buildings to live and breathe in. My name is Jess Kismet and I am your host. Today I am chatting to Villy Yordanov. Villy is a mechanical engineer who's all about problem solving and improving the world around him. He has experience in manufacturing and renewable energy and a real passion for sustainability and using his technical skills for good. He absolutely excels in his role as innovation engineer at Pro Clima head office in Sydney, and he has been a fantastic sounding board for me over the last 2 years with anything related to moisture management in buildings and WUFI. If you don't know what WUFI is, keep listening because we're going to explain what that is. Villy has most recently been working on solutions for concrete buildings, so we're going to dive into why getting this right is so important across all areas of the construction industry. So welcome, Villy. Thanks for joining me.
Thanks, Jess. Thanks for having me.
No worries at all. Okay, so as I said, you've been with Pro Clima for 2 years. So how did go back a little bit, give the listener a little bit of an idea of where you've come from. So how did your sort of career in building science begin, and how did you end up at Pro Clima?
Yeah, cool. My journey in building science, I think, began specifically within Pro Clima, but my journey within the built environment and sustainability goes back to my uni degree, I would say. So I grew up in Bulgaria, a small country in Eastern Europe, racing dirt bikes. And when I finished school, I had to figure out what to do and decided to go and study engineering in Denmark. And if you are familiar with Denmark, it was the country, perhaps the pioneer in renewable energy, specifically wind turbines. So just studying and being around the people and the culture, I got exposed to a very interesting mindset about sustainability and renewable energy and stuff. I ended up doing an internship at one of the biggest wind turbine blade manufacturers in Denmark, which was an amazing experience and really gained a lot of benefits for my future career as an engineer. But then decided to move on to Australia to do an exchange semester and haven't moved since. Came here for 5 months planning to study and married now with 2 kids and not going anywhere. But coming here, I moved into solar energy and working for a solar panel manufacturer, solar panels and batteries. So still being all around all this sustainability, renewable energy, wind, solar, etc. Then I moved into consulting, building services consulting in sustainability, or what they call ESD, environmentally sustainable design, where perhaps my initial exposure to the build industry began. You're working a lot with national construction code regulations, building projects of all kinds, etc., etc. And it wasn't until a few years later that someone said, "Hey, a client is asking for a hygrothermal assessment for WUFI. Can you please write a fee or something like this, scope for this?" And I know that the company I was working for was not keen on doing any of the hygrothermal assessment because of risks, etc. But one of the guys said, "Oh, hygrothermal assessment, talk to Jesse Clark from Proclima." I was like, "Oh, hold on a second. I've heard this name before. Let's check out what this guy is doing." Open Jesse's LinkedIn profile, and he just posted a job saying, "Hey, come work with me, innovation engineer." I read the job description and I'm like, "That's my dream job. I'm going for it."
Oh, wow.
And a few months later, with interviews and everything, I joined Proclima and felt like started from scratch, deep into the building science thing, specifically because, yes, even though I spent a few years in consulting within the build industry, that was not as much building science per se. As some of you may know, sustainability is not, depending on the company, I imagine, but it's not so closely related to many of the things we talk about when we say building science, like weatherproofing, air tightness, moisture management, etc. But joined Proclima about 2 years ago now, and it's been an incredible experience, learning every day and changing the world.
Yeah, absolutely. So you said that, I just want to clarify, you said that you worked at a solar, like the panel manufacturing. Are you talking about like the actual, the
Solar panel?
propeller looking?
Oh, that's the wind turbines.
The wind turbines? Yeah, sorry.
That's the wind turbines. Yeah.
Sorry.
Yeah, Vestas. It was one of the biggest until 2 of our smaller companies joined and they became the biggest. But Vestas was one of the biggest. wind turbine manufacturers. There are various sites all over the world making the different parts of the turbines, one being the blades. So each turbine has 3 blades. So that's where I was working in, new blade manufacturing. But there are different factories around the world that work on the tower, and the nacelle is what is called the hub that sits at the top where it attaches to the blade and is the actual thing that generates energy. But yeah, Vestas is one of the biggest companies in this field.
Yeah, that's crazy. I've seen them being transported like on gigantic road trains. They're so huge and so
Yeah,
just they look like they're from outer space.
yeah, that's right. And they keep getting bigger and bigger. It's incredible.
Yeah. Yeah,
Yeah.
so when people think of sustainability, that's, as you said, building science isn't what we typically first think of. We think of solar
Hmm.
or, renewable energy and carbon emissions and that sort of thing. So, yeah, your transition into building science with Jesse Clark, why was that with Proclima? Why was that your dream job? Like, what about it appealed to you?
Well, first of all, I get to sit to Jesse Clark shoulder to shoulder every single day. Yeah, which is the best thing ever. I mean, whoever doesn't know Jesse Clark, leading building physicists across Australia. Anytime a question comes in, I can freely ask him and learn from him. But yeah, that was one of the main value propositions. Work alongside me, come and break stuff, test things, hands-on experience. Like, yes, I'm an engineer, but as I said, I grew up riding motorbikes up in the forest, and you need to learn how to do these things yourself to repair stuff when it gets broken. So I do like hands-on stuff, even though I didn't have as much experience specifically building. But yeah, once you have a bit of hands-on stuff, you can figure out the rest. So yeah, hands-on things, apply things in practice, not just in the computer world, and yeah, just work for a greater good.
Yeah, that's awesome. That's awesome. So, what does your typical day look like at Pro Clima? What are you responsible for?
Playing every
Apart from
day.
answering,
Yeah,
apart from answering my questions
yeah.
that I try to do on a regular basis.
Yeah, it's extremely diverse. My role is called innovation engineer, so I'm innovating in a way, but it's so broad that I'm doing a lot of things. It's of course it's a lot of problem solving and figuring out how to solve all the problems we're seeing every day in the build industry, especially with both new but also existing homes, small homes, but also large buildings of all kinds. I do a lot of the compliance related stuff with National Construction Code when it comes to weatherproofing and condensation management. Also, when you, as a product manufacturer, when you do bring new products onto the market, they need to be tested according to certain standards. So I am the main person responsible to organize these tests, fill in any of the gaps that tests that need to be done when bringing new products in, ensuring compliance of all kinds of standards. But of course, testing ahead of time, not just for specific properties, but just for the application of the products we tend to use, um, figuring out different application of products. I mean, Proclima is a German-based company, German engineered, German made. We bring a lot of the products from there to here to Australia and New Zealand, but many times we have on our hands products that were made for the European type of building, which do not apply in any way to what we do here in Australia. So there are times at which we have to figure out how can we actually take some of those products and reuse them in a different way here in Australia for a different application, or sometimes find a used scenario where there is no such existing product and work with Germany collaborating to formulate a new product and create fill a gap that is here in the Australian New Zealand market. And in addition to all this, WUFI, I do, and we're going to talk about WUFI later, I imagine, but WUFI, hygrothermal modeling, we are the company that works with the Fraunhofer Institute, who has the background of WUFI. So we are the ones who do all the training. So I do a lot of the trainings with professionals, architects, designers, engineers of all different levels, fundamentals up to advanced two-dimensional. And yeah, I also go around to sites to advise on our application of our products. And here and there, I do some presentations one-on-one with architects and facade engineers and presenting at larger forums and conferences and expos and stuff. So yeah, extremely diverse, and that's why I love it.
So you've got a strong background in engineering. How have those skills translated into the work you're doing now in building performance and moisture control?
That's funny you ask this. I was thinking about this the other day. I remember my first day of engineering school. We had a guest lecturer that, or a guest alumni, I would imagine it was, who basically introduced to us that said, guys, look, you're going to study 4 years of engineering, and you need to remember from day one that when you finish that degree, you're going to go and start to work in the industry, and you're going to use no more than 5% of what you've studied. So take this into account, yeah? And I was thinking about this the other day, and I think I am using or utilizing in a way probably 90% of what I studied in engineering as a mechanical engineer. Material science starting from year one, but also thermodynamics, heat transfer, fluid dynamics, air conditioning stuff, which is based on all of the things I had before. Of course, 3D modeling, creating renders and different designs, technical drawings, main factor in my job, how to read and understand technical drawings. Yes, mechanical drawings are different than architectural drawings, but once you understand one, you can quickly adapt to understand the other. So yeah, when you start studying mechanical engineering, you don't really know. You probably think you're going to go into HVAC here, for example, in Australia. It's quite common, but
Yeah.
back in Europe, you imagine you're going to start working for a car manufacturer, and that's all your scope of work could be. So I would have never thought that I would end up in the building science field and utilize everything that I've studied almost to a full.
Wow, you must be one of the only people who can say that.
Yeah, exactly. Probably.
Most degrees, I can imagine, mine included. You don't really, you learn everything on the job. You get the bit of paper so you can get the job,
Mm.
and then you learn on the job. So that's
Yeah.
really cool. So the work you're doing in WUFI, let's actually move on to that because I'm sure the listener wants to know what this weird named thing is. So could you explain what WUFI is and the connection with the Fraunhofer Institute and how it's integrated into your work?
Yeah, for sure. So WUFI, I'm not gonna even attempt to pronounce the exact German word of what the 4 letters stand for, but it's technically meant to say heat and moisture transiency. So if we go one by one, heat, obviously temperature changes, moisture, humidity changes, or moisture changes, and then transiency implies that this is being simulated on an hourly basis. It's not a steady state condition, one condition on the inside, one on the outside, and that's it. Transiency means we simulate 1 hour by hour. So hygrothermal modeling, we're simulating moisture and heat movement within assemblies to assess the risks of mold and condensation and long-term water damage that could occur within assemblies, whether that be timber frame or steel frame, rotting, corrosion, etc. In a nicely, simply designed software by the Fraunhofer Institute of Building Physics in Germany, which is, the creator of this tool back in the 90s or 80s or 90s when they started repurposing or retrofitting a lot of buildings, and they had to figure out, once you start insulating something that was not insulated before, could that cause new problems? And WUFI was developed, and
So WUFI was developed directly to solve the problem of insulating old buildings.
that was my initial understanding.
Yeah, right. That's interesting.
Yeah, but yeah, Hartwig Kunzel, the godfather of WUFI, the creator of WUFI, is the man behind, and he's very active in this space to this day, still working for the Fraunhofer Institute of Building Physics. And then yes, Pro Clima in Australia and New Zealand are the official, you can call, partner of Fraunhofer for supplying WUFI, technically with licenses, and get a kickback from that based on trainings and support that we deliver to the market.
Mm-hmm. Mm-hmm. I actually met Hartwig before I really knew who he was. Jesse got him to the Building Physics conference. I think it might have even been the very first one I ever went to.
Oh yeah,
Yeah.
Aero
So I
Building Physics
actually,
conference. Yeah,
pardon? Yeah,
Aero Building
he
Physics.
came.
Yeah,
Yeah, at the ARA. Yeah, he came
yeah,
over to Australia and he was one of the speakers.
yeah.
And I wish I'd understood more of who he was and his work because I
Oh
would
yeah.
have. Yeah, I didn't really. I was. This was in 2018 when I'd been in the energy efficiency game for a while. But that conference was the beginning of my sort of journey into the building science.
Hmm.
field,
Amazing. Yeah.
specifically building performance field. That was like a, opening of the doors for me, that particular event, and he was there. So
Yeah,
yeah,
pretty cool. Yeah, I know he did
pretty,
present not last year, the year before, but yeah, didn't manage to come in person. It was all online. Yeah.
yeah, yep,
Yeah.
yep, yeah. It can be hard to get them all the way over here.
Mm.
So it's a hygrothermal, so heat and moisture, and it predicts a mold index, right? So
Hmm.
it gives us an idea of what the risk of mold appearing in a particular area of a building. So it doesn't assess. I often get asked if WUFI assesses a building as a whole, like, will my building go moldy?
Hmm.
And it's not really for that, is it?
Well, there is a software called WUFI Plus, which you can do a whole building modeling, but
Okay.
you would not really do it to answer that specific question. Would my whole building go moldy? You would focus on risk areas in a conservative manner. You would grab certain one-dimensional sections of a wall, of a roof, or a slab if you're gonna have, if it's worth simulating, if it's a complex scenario. And yes, depends on how deep you want to go and how unique and perhaps different your design is to what the industry is used to seeing and knowing what works in practice. Perhaps utilize a two-dimensional calculations across slab edges, window junctions, wall to roof connections, etc., where you have a change in a geometrical shape where two surfaces at different angles meet and two different materials meet at different angles that could create potential issues from moisture accumulation or thermal bridging, cold spots, etc.
Mm-hmm, mm-hmm.
But to
So
answer the
my
question, would your whole building go moldy? I don't think it's a very easy, straightaway answer.
No, no. I think it's just a misconception in the
Mm.
sort of industry that people think that that's what they're going to get out of that assessment. But no, it's the most common WUFI assessments. The ones that I do are the 1D, and
Mhm.
they are simply of one build up, one
Mhm.
wall system, one floor system, one roof system. I've
Yeah.
tried to do the 2D, and I only had the license for 1 year. I think I only really did one job with it.
Mhm.
Do you think that there is that the 1D simulations can cover most scenarios with sort of safety, like
Dep
safely make an assessment?
yeah, it depends. Actually, that's how we begin our two-dimensional course, talking about when would you even go for 2D and when is 1D insufficient. And one of the first examples we give is take a section or like a plan view of a typical stud wall. If you are to simulate a stud wall one-dimensionally through the insulation layer compared to one-dimensionally through the timber layer or the steel stud layer
Mm.
compared to two-dimensionally across the whole assembly, you would find sometimes that the simulating it through the insulation layer is the most conservative scenario, and a one-dimensional simulation gives the same results as two-dimensional, which leads you to understand that 1D is sufficient. You don't need to go to 2D. Then you start overlaying a scenario where you add an additional layer of insulation on the outside or an additional layer of insulation on the inside within the service cavity. And in that case, your steel structure is, or your stud framing structure is either on the warm side or on the cold side. And you start seeing that the difference between 1 and 2D becomes apparent in some of these cases. Then you apply this to a more complex junctions like a slab, where an insulated slab edge cannot be taken into account into a 2D into a 1D scenario, and then the answer is that 1D is never going to be enough for that specific junction. So yeah, for the most part, the typical wall constructions that we use, 1D through the insulation layer is the most conservative way you can do things. But once you get into the junctions and the complex sites, 2D is a better tool to use.
Okay. The license is a lot more expensive though. I think it's, for a practitioner, I think it's double the price of a 1D
Yeah,
license.
yeah,
So yeah,
yeah. But the
in our
license,
in
of
our
course, the license is gonna be expensive, more expensive because it's a lot more complex too. It's a very different
yeah.
way of calculating. But the bigger implication to someone like a consultant who's going to be using this tool is the computational time. Especially in the latest version of WUFI 7, a 10-year calculation of a typical wall assembly can take a minute. A typical 3 to 5 year two-dimensional simulation, it's upwards of 10 hours.
Yeah,
So
I left mine going overnight several times.
yes, you normally run
And
overnight unless you have
yeah,
really powerful computing power.
yeah,
But yeah, so because of this, you can run 10, 20 different iterations to advise your client on various options of insulation thickness, location, type of membrane, inside, outside, etc. You can't afford to do this on a two-dimensional scenario. You're just gonna run out of
no,
time. Yes.
yeah, it'll get expensive really, really fast.
Yeah.
100%.
The bottom line is that at the minute, there's no one forcing you to do 2D instead of 1D
Yeah,
to meet compliance with the building code. So for the most part, if you do want to follow the performance method and use the verification pathway of performing a hygrothermal simulation in WUFI, a 1D simulation is technically sufficient to meet building code.
yeah, yeah. So to clarify what Villy's talking about, the WUFI can be used as a verification method or an alternative performance solution in the condensation management section of the building code.
Yeah.
So you can do, for example, in a wall build-up, you can use a certain type of membrane depending on your climate zone. Or you can do, if you don't have a wall build-up where you can use a membrane, or you don't want to use a membrane, you can do a WUFI simulation instead and prove that your wall system won't go moldy at the critical point. So it's just sort of a flexibility the building code offers now. Something where a homeowner can say, this clause, you said that this building wouldn't go moldy because you did this and it did go moldy, so this is your fault or someone's fault.
Yeah. Okay. So you need to look at what the objective and the performance requirement of the specific clause is. In the condensation management provision specifically, it does state that anything that's going to have an impact on the health of occupants or loss of amenity. So yes, if mold does occur, technically the objective of that clause has been breached and someone needs to be held liable for. And then it begins the discussion, who is liable? Was it the designer who put it this way? Was it the architect? Was it the consultant who said it's going to be that way, but it ended up being otherwise? Or was it the builder that didn't install the things well the way that the designer specified that they should have been? And that's where things get tricky and
it gets complicated, and that clause hasn't been used yet. And until it does, we won't really have any precedent. But it's I think it's enough of a indicator that the legalities, like the legal requirements, are closing in around building health and building performance in a way that is no longer something that can be ignored. Would you agree?
Yeah, absolutely.
Yeah. Okay, concrete.
Oh, okay.
Push. So you've developed a real specialty since you've been at Pro Clima in moisture management in concrete structures. I know that we know that concrete has a really, really high percentage of water when it's poured, and then some of that evaporates over time. But concrete holds a lot of moisture in it inherently because of the way it's made. So what have you learned about concrete, and what is it that makes concrete such a unique challenge?
Yeah, you're right. One of the main things about concrete is that what Joe Stiborek describes as a moisture reservoir. It stores a lot of moisture within its pores. But that may not necessarily be an issue if you have allowed it to evaporate ahead of time and cure sufficiently. What the biggest challenge with the typical precast concrete construction, and that also applies to in situ concrete, but also all the permanent formwork solutions we are seeing pop out left, right, and center in buildings where you have a sandwich of few panels, for example, fiber cement panels, and you pour the concrete in between and you leave it as it is. The issues with these type of assemblies is the material properties of the concrete in general, and specifically how air and also vapor impermeable concrete is. There is no drain and ventilated cavity in a face-sealed concrete assembly. So when you have a lot of hot, humid air from the indoor environment trying to escape through the building envelope towards the colder side, towards the outside in winter, you have vapor passing through the plasterboard lining, passing through the insulation layer, and gets in contact with the cold surface of the concrete and has nowhere to go. There is no drain and ventilated cavity. The concrete is highly vapor impermeable, and When hot, humid air gets in contact with cold surface, not good things happen. And this is where we see the condensation on the inside face of an interiorly insulated concrete being a very big issue in our industry.
Do you have any photos of this?
Yes.
Are you willing to share them?
Yes. I have
Yeah.
I do have a photo even on from my building physics conference preso from ERA that we had mode image on concrete building in Canberra. I can obtain a few more from a few engineers have been sharing some horror stories lately, talking about the amount of moisture condensing on the concrete and draining down into the slab, leaking through the bottom plate of the stud wall into the plasterboard, wetting the carpet of the indoor space. Yeah, liters of water. Yeah.
Yeah, I've been made aware of a project that's being worked on by a colleague of mine recently where they've just created concrete bunkers here in Adelaide. So not climate zone 6, but climate zone 5. So it gets cold enough during winter.
It's cold enough.
Um,
Yeah.
yeah, and they've just created these concrete bunkers and they're set into the ground as well. So they're retaining walls. So there's
Yeah.
just nowhere for the moisture to go at all. Obviously, that's waterproofed on one side, but habitable spaces inside concrete bunkers inside the earth. I was sort of talking about this with my colleague and just went, oh my goodness. I mean, will that earth keep that concrete warm, do you think, in that situation?
I don't think so. It will keep it
No?
where the slab is. That's why many passive houses get away without any floor insulation, where slab is sufficient, but not on the walls. If
Yeah.
anything, if things are not done well, you can promote further movement of rising damp through the concrete, wetting it
Yeah.
continuously through groundwater.
And how do we go about solving this issue?
Yeah, complex question, and many people don't like to hear the answer. The ultimate solution is, drum roll please, put all the insulation on the outside. Yeah. Put all the insulation on the outside, keep that concrete warm, utilize the thermal mass the way it was meant to be utilized in the first place, and yeah, keep the concrete warm. Hot, humid air is not getting in contact with the cold surface. Chances of condensation are almost fully eliminated depending on climate zone. But yeah, much better design approach. The way a concrete building could be built anywhere in Europe, for example. But why do people don't like this, or why do architects and developers and designers don't like this? You hide the concrete look, which is the first thing behind going for concrete in the first place. Yeah, you're gonna cover it with an exterior grade insulation to keep it warm. You can put some sort of cladding on the outside, perhaps cladding that looks similar to concrete, but then you can ask yourself the question, why concrete in the first place? You could have done exactly the same thing with a lightweight steel frame or timber frame if you wanted to do this on a resi scenario. So that's the ultimate solution. Other solutions.
It's also quicker, right?
That's the other idea. Yeah, that's the other reason why people are going for panelized precast concrete panels. It's much quicker to install for sure. Yeah. But yeah, so what's the other solution? Put a vapor impermeable insulation on the inside face of the concrete. This is normally a closed cell expanded or extruded polystyrene, which is a vapor barrier. So you don't allow the vapor to get in contact with the cold surface. You stop it at the insulation layer. Of course, you need to tape each of these boards with the vapor barrier tape. There is one problem with this. It's combustible. You can't install it in buildings higher than 10 meters high in a commercial scenario. If you really want to build a house out of concrete, you can do this in a single dwelling house, but anything high rise, no go without a specific fire engineering solution. And the last option, which is what we as Proclima have been trying to figure out and how we can solve this issue without going to the externally insulated extreme, is putting a vapor control layer on the inside of the insulation layer. This is the Intello Plus intelligent air barrier, where the idea is you do stop the vapor going through the membrane in winter so that the vapor behaves as a vapor barrier in the colder months where humidity indoors tends to stay low. So you don't allow that much vapor to pass through the insulation layer getting in contact with the concrete. But then in the hotter, humid months, especially if you do have some moisture within the concrete that's being pushed inwards. So again, from hot to cold, you go from outside towards the inside in summer in terms of vapor drive. The membrane opens up, becomes highly vapor permeable, and it allows that vapor to diffuse to the indoor environment so that it prevents it condensing within the wall assembly. And yeah, this is a solution we've been doing a lot of work in the background, trying to figure out which climate zones it's going to be a suitable design approach to do and what can be done about it so that people don't have mold in their wall assemblies but can still keep their concrete where it is.
It's time for a quick sponsor shout out. Today's episode of the Building Sciology Potty is proudly brought to you by our amazing sponsors, Enduro Builders and Climasure. A huge thank you to these incredible businesses for supporting the podcast and helping us spread the word about better buildings to live and breathe in. Your support makes this podcast possible. Please head over to their websites and follow their social pages. Yeah, so that would seem to be the simplest solution, right? Would it be in Tello?
Well, simple on paper, but once the practical side comes into play, you need to know what you're doing. You need to plan well ahead of time, and you need to do a good job installing that membrane in order to be doing its job as intended. Because the membrane will behave as a vapor control layer as long as it's a nice and airtight install.
Complete.
Yeah, exactly.
Yeah, that makes sense. And the all of this advice that you're giving, you mentioned climate zones before. So externally insulating concrete or internally insulating concrete, is there one that's better in the warmer climates or colder climates?
Well, from a lot of the hygrothermal simulations we're doing for this specific scenario, I've seen that Brisbane specifically is okay, solely from the purposes of reaching National Construction Code compliance for its mold index. It seems like
insulating?
For internally insulating concrete. Yes, because it doesn't get cold enough. The concrete doesn't get cold enough to the point that condensation forms for too long. And yeah, Brisbane seems to be okay. Anyway, Brisbane and anything north of Brisbane, basically.
Okay.
Anywhere south from that, including Perth, where we see not so cold winters and relatively dry weather. Even in Perth, we see a lot of issues with internally insulated concrete. But yeah, where does external insulation begins to work? Well, technically, again, Joe Stiburek, perfect wall. Put all your thermal, air, water, and vapor control layers on the outside of your assembly, and you can put that assembly anywhere, and it's gonna work.
Yeah. Took me quite a while to understand that perfect wall.
Yeah,
all the different layers and why that, because in Australia we put all sorts of layers on all sorts of places in the frame, insulation in the frame, and when I did understand it,
it clicked in it. Yeah,
it makes sense.
Yeah, exactly.
Keep the structure warm. For
it makes
sense.
Sake. Why don't we build it like that? Yeah.
Pardon?
Why don't we build it like that if it does make so much sense? Yeah, it's a big issue. Biggest question. Yeah.
So the perfect wall, I'll put a picture of what we're talking about on the screen so people can see what we're talking about. But you've got all the layers on the outside of the frame. Can you still insulate inside the side frame?
Sure, you can. You have a lot of hollow space there that you can fill in with insulation and might as well utilize it. But what I've recently, for example, talked to some of the North Americans at a recent Building Science Summit in New Zealand, they said they stopped putting any of the fibrous cheap insulation between the studs. Everything sits on the outside as a perfect wall. I said, why? I said, well, it's a waste of time. You have such a high thermal highway through those steel studs that as much as insulation as you put in between, you lose a lot of the effectiveness due to thermal bridging. So might as well not waste your money and time and just put everything on the outside, which is ironic to hear, given that that's all we do here in Australia on a 90mm frame. Yeah. But if you take Germany, for example, you would still find a typical lightweight structure with timber. I don't think you'll see steel frame there like that, but timber frame in a typical residential scenario, much thicker walls, not 90 or not 140, much thicker walls filled with fibrous insulation and external insulation as well. So They have a certain guidance as to how much is in between the studs versus is how much on the outside of the studs. It's a safe scenario from a condensation point of view. But yeah, they certainly utilize those really big studs that they have to fill them in with high quality fibrous insulation.
How big are they? How thick?
Well, I don't want to quote the German carpenters here, but upwards of 200 mil. It's thick walls, thick, big, stable, solid, stable structures.
Yeah,
They
right.
could, I mean, talk to any German or European, as
Yep.
a matter of fact, coming into Australia and seeing a 90 mil frame erected into a building site. They're like, is this an internal wall or what? Even internal walls could be somewhere quite thick. Yeah.
Yeah, I don't. Uh, anyone who comes from overseas to Australia comes here and goes, "What the hell? What the heck is this? What are you doing here?"
Hmm.
Um, and I guess we just take it for granted.
Hmm.
Um, in your experience, what are some of the most common misconceptions about moisture in buildings?
Moisture in buildings. Okay, common misconceptions. Here is an interesting one that I keep saying every single day, and it took me a while to get what was happening until I realized that people are completely confused. When people see the magic line of hope annotating the pliable building membrane that sits on the outside of a building, and if you ask many of people, what is this? What do you put this membrane there for? Many times the answer is, oh, you put it for condensation, to stop condensation. I find this as a big misconception in the industry. The pliable building membrane that goes on the outside of the structure is not to stop condensation. It's for weather protection. It's called a
Yep.
weather resistive barrier because it resists the weather. The risks of condensations are much, much lower compared to what we used to use there, being shiny aluminum foil, the perfect vapor barrier where condensation will definitely form. But this membrane is not installed on the outside of the structure to stop condensation. It's installed to protect the structure from getting wet in the first place, which is your main priority. The main priority is if you want to stop water ingress from the outside. Priority of 1000. Priority of 100, passive house style principles. Priority of 100 is your air tightness layer, prevent accidental air leakage, improve energy efficiency, energy leaks, moisture leaks, keep your structure airtight, basically prevent the effects from wind washing from the outside to affect your insulation effectiveness. And then vapor diffusion and the risks of condensation comes next.
Yeah,
But
I agree with you. I think that is one of the biggest misconceptions because the reason that we introduced, or the reason that the industry uses these membranes in the first place, is to protect the frame from the weather during construction. That was why they were introduced.
mm,
And it became a problem because we were using foils that was trapping vapor.
mm,
So
yeah,
that is why the requirements for vapor permeability of these membranes has become an issue. The whole purpose is, as you said, to protect the frame from the weather. And that is why when you see torn, ripped membranes, in developments or on a construction site, it's
yeah,
a
you might
complete
as well
waste of
not have put
time.
it. Yeah,
You might as well not have put it there because it's doing
yeah,
absolutely nothing.
exactly. Yeah,
Investing in
and
a good quality membrane and proper
mm,
install is the only way that's even worthwhile doing.
yeah, exactly. And just to clarify, yes, of course, it's a main priority to protect your structure during construction because that's when it's going to be the most vulnerable before any cladding or before any roof structure is go over it. But you also want to keep your structure dry during occupancy for the next 50, 100 year of whatever your planned building life is.
Yeah.
And even though you may have protected your structure well during construction, you don't want to remove this protection once the building is fully cladded over, because water will find its way through. There is enough studies to show that rain under wind-driven situations, what we call wind-driven rain, will find its way past the cladding and it's going to try to get into the interior, wetting the structure and causing long-term damage if not attended to on time.
Yeah, definitely. And that's usually, I did a post just recently. It was a quote from Joe Stebrick himself. He's been mentioned a few times today. Uh, a quote from him: "Repeat after me. All claddings leak. At some point, they're going to
Mhm.
leak. Whether it's
Yeah.
through the joins, whether it's through window openings,
Mm.
through they're just." eventually, over the life of the building, water ingress will happen.
I think the quote was about windows. It says there are two types of windows, those that leak and those that will leak.
Yeah.
That's it.
That's another
Same
one.
with the
Yeah.
cladding. Yeah.
Yeah. So, water is not good for buildings. And
No.
the membrane is a crucial part of protecting the structure and the durability of that structure.
Yeah, absolutely.
So yeah, good one. Good tip there, Billy.
Mm.
How do you approach balancing air tightness and vapor control, especially in our warm, humid Australian climates up north?
Do the perfect wall, end of story. Now,
Yeah, done.
yeah, the thing is, it's quite challenging. And yes, while we do have many off-the-shelf solutions that people are going for, I think it's really a case-by-case basis. Depend really, of course, mainly climate dependent, but not just because you're in climate zone 5 and not 6 or whatever. Also, microclimate, like are you on a hill? Is it a wind-driven rain? Where is the wind predominantly coming from? Like these are things that ideally someone should take into account early on when planning the building for optimal, healthy, durable, energy efficient performance of your buildings. But from there, we have varying climates in terms of how cold they get in winter and how humid they get in summer. And dealing with this is not a straightforward off-the-shelf solution for every situation. So it's really case by case basis, and we try to help as much as possible based on where the climates are and the type of construction that's being utilized, but very challenging for sure.
I thought you said the perfect wall was the solution.
The
Off the
perfect wall
shelf
is the
solution.
solution. It's just not an
Yeah.
easy sell for most people because the
Yeah.
walls gets thicker. The insulation that goes on the outside is not cheap. The
Mm.
way you hold your cladding, whatever you want to be on the outside, needs to be carefully planned ahead of time to how you're going to hang it off that far away from your structure because you have such a big insulation sitting in between. How you're going to transition from your wall to your roof without interrupting your rafters passing through. All these things are doable. We know how to do them, but they're not standard details to what architects are used to.
Yeah, it's a big education piece. Just getting them to detail vapor permeable membranes correctly is challenging enough.
Mm-hmm.
On the upside, though, I have been doing some talks to uni students lately, so
Oh, amazing.
this sort of stuff is making its way into unis now, which is positive. And your comments earlier about actually using your uni degree, I'm hoping that that this sort of stuff will start to be integrated into architecture degrees and construction management degrees as well, so that these up and coming site managers and architects can use some of what they
Yeah.
learned at uni as well.
Like it's done overseas as well. I'm pretty sure many of the architects overseas study these building science principles in great detail, not just the fancy aesthetic stuff. Yeah.
Yeah. It's not, if you're building a building, you're dealing with heat, air, and moisture, no matter whether you are or not. So
Mm-hmm.
it's just building. It's not building. I mean, it is building science, but it's also just building. Understanding this stuff is fairly important to understanding construction in general.
Exactly.
Have you had a particular case study or project that really highlighted the importance of getting moisture management right? Have you had a lessons learned stuff up?
I wouldn't say a particular project. A couple of things spring in my mind straight away. Obviously, lessons learned from all over the world over the last few decades. The leaky condo crisis in North America and the New Zealand leaky building crisis that cost many, many billions of dollars in damages and health implications to occupants is well documented and can't be emphasized enough how important it is to sort this water ingress out from the structure early on. But what I also come to mind is all the cross-laminated timber buildings that come every now and then lately, popping out on projects targeting low embodied carbon emissions and all these kind of sustainability initiatives. Well, timber, it's great, until it gets wet for too long. So these type of buildings, we need to make sure that they stay protected all the time from the factory up until the building is fully occupied. And we see some not so perfect approaches for this on site on some of these timber buildings where protection was not done on time or not done at all. And you may survive one rain event, and after the second, you're in big trouble. And all the carbon emissions you thought you've saved because you've used a lot less carbon intensive material being timber compared to steel and concrete will get completely blown out of the water when you draw the line and see how much energy and chemicals you had to use to dry that timber and clean some of the stuff that happened to the timber that you didn't want to happen.
Or potentially replace some of it, right?
That's a big job and probably a lot more cost, but yeah, you don't want to go there. And if you speak to any person dealing with mass timber structures, they are becoming more and more wary and aware of the consequences, and they do anything about it, to anything that in their power that they can stop it.
Yeah, right. So timber's treated though, right? The timber that they use is not just raw timber. It's been impregnated with something, or it's been, I'm actually reading Rotonomics. You mentioned the leaky building crisis in New Zealand. I'm currently reading the Rotonomics book, and I'm learning a lot actually about history, because it's kind of closely linked to Australia as well, like the history of construction in New Zealand. So it's quite relevant, and I'm sort of learning about some political decisions and things that led to this leaking building crisis, as well as industry and regulatory decisions that were made. And one of them was how the timber was treated and what types of timber they used. So in the mass timber industry, is there a certain type of timber or a certain type of treatment that is only allowed?
I am not an expert and I don't know these things. I know that Germany has moved years ago into fully untreated timber. So the argument is timber begins to rot, mold begins to grow if you give it the right conditions of moisture and food source. If you keep everything dry, these things should not happen.
Okay.
So the approach is
they perfected the art of keeping it dry.
Yeah, exactly. Protect everything ahead of time in the factory, and once you build under big tents and teepees, and the second rain drops, you clean it straight away, or you squeegee it out of the building. You have floor drains positioned every so often across every floor plate, so that no water gets in contact with the timber, because not good things will happen.
So they're choosing to keep the chemicals out of the timber and choosing to be proactive about how dry they keep it instead.
Exactly, yes.
Yeah, wow.
It's a hard sell for the tropics if you're gonna have constantly exposed high humidity environment, and also termites. You do want to do something about that, but that's different topic, and again, not something I'm an expert in, but all kinds of opinions there.
Yeah, I'm interested in digging into that a little bit more deeply at the moment. So if anyone, if you're listening and you have experience in the timber industry, send us an email or comment on this podcast. I'd love to talk to you. What trends or innovations are you seeing in the building science space that you are particularly excited about?
I think we're starting to move into the right direction. We start to see facade engineers, specifically for high-rise projects where you do deal with a lot high wind pressures, and weatherproofing is front of mind as again, first order of priority, stop the water coming in. And people are realizing that in these high wind environments, flexible membranes are not enough. They flex in and out of the building. You don't know how long the fixing points will last, and you need to move into a rigid board solution of some description, protected as well, either taped at the joints or ideally fully protected with an adhesive membrane. So we are seeing the push towards state-of-the-art rigid board solutions, and in some applications with exterior insulation on the outside. It's going to take a while to become a common practice, but we are starting to see projects pop up, and we hope we see this move into the right direction in the future.
So you're seeing this move more into the commercial space, not just into the not just coming from the residential space. Is that what you mean?
Yeah, definitely in the commercial, because there's a lot of exposure we have in there, but in the residential space a lot. I mean, the passive house movement has gained quite a bit of momentum. We see a lot of passive house projects coming up, following full design principles on weatherproofing and air tightness and vapor control, which is incredible to see. But we start seeing also a lot rigid board solutions on the outside, but sometimes also on the inside, that originally used for bracing are now applicable also for high wind zone pressure weatherproofing systems and air tightness.
So could you, for the listener who doesn't understand what you're talking about, could you explain a bit about what you mean about
Yeah,
the rigid boards?
so when you have a typical lightweight construction where your structure is comprised of timber or steel framing members, you have options how to protect it on the outside. Normally you staple onto the timber or you screw onto the steel a typical pliable building membrane, which ideally should be installed nice and taut and well, but wind will blow onto that building. When the wind blows towards the wall, the membrane will bulge inwards, basically compressing the insulation that's in between the studs. When the wind blows from the other side, the melting will bulge out from the building, perhaps minimizing the gap between the cavity or getting in contact with your cladding or your bricks or whatever is in front of it. And this happens millions and millions of cycles over the lifetime of the building, the membrane going in and out like a parachute. And there is no long-term studies or any tests that could prove how long a typical pliable membrane lasts in high wind exposure environments. And that's why many jurisdictions actually have reinforced overseas the use of a rigid substrate. That could be an oriented strand board or plywood in the residential context, but that's combustible. It can't be used in high-rise applications here in Australia. So we move to a non-combustible solution such as fiber cement boards or exterior grade gypsum boards. So you put those boards on the outside of the structure, and then you need to protect them at least at every joint where the panels meet each other, but perhaps fully protected with an adhesive membrane fully throughout, so that if any water comes in, the structure, the boards, and the framings are protected. But when wind blows, the board does not deflect in and out like a parachute. And the water, the connection points and any compromised points at which water can find its way through the building are greatly improved.
Mm-hmm. Yep. And that plyboard or OSB, two questions. Do you have a preference or an opinion on which one is better from a moisture control perspective? And two, how does that change the vapor permeability of the wall system? Because obviously the membrane and that substrate are going to behave differently to a pliable membrane.
Yeah, so these two questions actually quite interlinked together. So how much would the vapor permeance of the full assembly will change when you start introducing a board will depend on the property of this board. And do I prefer ply or OSB? I don't know, because I don't have a very clear picture on the material properties of these materials in Australian context. We know that in general, oriented strand board 3 tends to be a lot more vapor permeable than most plywood and more permeable than OSB4 just because of the types of adhesive used. But the type of timber and the types of adhesive used between the different veneer levels of layers of plywood could determine how permeable the plywood itself can be too. So I do not have a preference from my side, and that's not something I could enforce as a product supplier of membranes. But yeah, the ultimate goal is that we're going to get some material data of Australian-made OSB and plywood boards. But in general, once you start introducing a rigid substrate and adhesive membranes into the structure, you start adding vapor resistance. And again, going back to concrete, when you have a layer that sits on the cold side of the insulation that vapor can't freely escape through, you may have risks of moisture being trapped on the back side of that rigid board system. And if left for too long, mold could start grow, rotting may begin. And these are the type of system where you do one thing, you do install the board for long-term durability from wind exposure and also bracing elements, structural stability, etc. But then you start questioning condensation risks, and then brings into the question, well, how do you solve this? Either vapor controller on the inside and or an external insulation layer on the outside to keep that board warm. Again, both resi and commercial, same application.
So moisture management comes down to basically keeping the external layers warm or stopping moisture from getting to the external layers.
That's it.
In a nutshell. So I did the Building Science Fundamentals course with the illustrious Dr. Joe Stebrick earlier in the year. And he says that ply is better because ply, as it gets wetter, gets more vapor permeable.
Mm-hmm.
So this confused me because I had heard that without some, you said there's not a lot of data in Australia, so we do need some more reliable data. But I had heard just that OSB was actually better than ply. Ply was going to go moldy a lot more quickly. So that was the information I had. And then I heard Joe Stebrick say that that ply was actually better. So I was questioning this, and then I was told that the glue layers and the chemical makeup of ply in America is different to Australia. So this has been a bit of a confusion amongst some people I have spoken to. Do you have anything to add to that?
This is not an easy topic, but 100% there is so much variance in the type of timber, but the type of adhesive that's within those type of materials. In general, when timber gets wet, it becomes more vapor permeable. So the fibers open up and allow the movement of vapor to move freely through. So how much timber is in ply compared to how much timber is in OSB? Many times OSB has a lot of glue in addition to timber.
Right,
so that glue would really determine what's going to happen once stuff gets wet. But to make things even more complex, the vapor permeability of timber changes based on the history of timber wetting. If you've had many cycles of how often that timber got wet and dried and wet and dried, and you keep testing the vapor permeability, you're going to get different answers. And this brings big unknowns as to what's happening. How long is the ply that you're about to put in your building been in the warehouse, gone through a few winters of really dry weather and a few summers of extremely high humidity, and just by simply sitting in the warehouse got wet and got dried just to try to equalize the levels of moisture within. But on average, you expect that timber does get more permeable when it gets wet. And the type of adhesive will change this.
So this is another example of how computer simulations and reality don't always line up, because we put OSB or plywood into a WUFI simulation and we base our simulations on the properties inside that software. But actually in reality, the material that we use could be quite different. The material that gets installed could be quite different. Just because of how old it is or how many times it's got wet. Would you say that's true?
Yeah, absolutely.
Yeah, right.
That's why you make conservative assumptions and you validate studies from various material sources and in like real life experiments, which Fraunhofer has done to validate the needs, how closely computer simulations correlate to reality. And many times, even though, yes, there are variations in reality, they are not so significant to the point that you're going to get a completely different result from your calculation. But in general, calculations are never perfect.
Yeah. But you have a fair faith in the ability of WUFI to make good conservative assumptions based, rubbish in, rubbish out, right? So, the person doing the assessment has to understand what they're doing. But if they do understand what they're doing, you're fairly confident in the simulations.
Yeah, for sure.
Okay. For engineers and designers who want to understand more about this stuff and level up their training, where do you recommend they start?
Honestly, go and read the Pro Clima study on air tightness and moisture management in buildings. It is not a small book. It is half a physics textbook and half a practical guide on how to do stuff. It's going to take you a while to go through, but you're going to learn a lot. And if you don't want to spend all that time, go and watch 2 YouTube videos, which are the summary of that study. One by Jesse Clark, one of the main authors of the study, and one by our German master carpenter, Daniel Jacobs, talking about the practical side, where we did a roadshow of this study and they presented and we did the recording and it's now on YouTube. So 2 videos, 40 to 50 minutes each. You can get a good glimpse of this. If that's not enough, proclima.com.au/technical corner. Go and read all the articles there. Come and do some WUFI training with us if you want to learn more about WUFI and how to use it, how to apply it in your job. And if you run out of this, go and ask Jess about Joe Stiburek's courses and articles and rotonomics books.
Yeah, that's where you go from there. That's it. That's absolutely
it.
Yeah, highly recommend. Again, all of those links will be in the show notes. So please, if you're interested in learning more about moisture management, in hygrothermal analysis, in anything to do with Pro Clima membranes, moisture management, air tightness, weatherproofing, weather control, all those sorts of things, please look at the show notes. There'll be some really good and relevant links there. Final question, Villy. I asked this question of everybody. What is the one thing that you want people, the person listening, what is the one thing you want them to know?
I've listened to all your episodes, so I knew you're going to ask me this. And here is what I think I want to say. Be aware that when trying to solve one problem, you may be creating another. We learned this the bad way when we started putting insulation into our buildings to make our buildings more energy efficient. And then we realized that when we put insulation, some things stay colder than others, and that's when condensation happens. So view your building holistically, whether you're an architect, designer, engineer, or builder, and question, if I make a change here, could that lead to a change elsewhere? And if you don't know the answer, try to ask people that may know the answer. We've had lots of years of experience, and we've learned from many years of failures that we don't need to repeat again.
100%. Unintended consequences, and they can bite you on the butt. And there's lots of overseas lessons that we can learn. So.
Yep, absolutely.
All right, Villy, we will wrap up this conversation there. Thank you so much for joining me. I really appreciate your time and your expertise.
Thank you so much, Jess. Pleasure to have you.
That is all for today. Thanks so much for tuning in. There'll be another episode in a fortnight, so if you would like to listen into the types of conversations that I have all the time, please subscribe on your chosen platform. Rate the show, leave a comment, whatever you like, share with your friends and family. I'd love for you to spread the word about the Building Slayology Potty. There's a link in the episode description where you can head to a landing page, and there are some show notes there with relevant links and a full transcript of the show as well, and also links to my socials. So if you're not already, I'd love for you to follow along there too, as I share lots of building science and building biology tips. There's also a contact page where you can send me an email or even a voice message. So if you've got questions or suggestions or guest ideas, I'd love to hear from you. I want to know what you want to know, so please get in touch with me. Thanks again. I'll be back in 2 weeks. So until then, happy, healthy building.